Jnanam Paramam Dheyam. Knowledge is supreme.
So, good afternoon. I want to continue from the last lecture. We proved dimension theorem and we were deducing some consequences of dimension theorem. Today actually I will concentrate on proving so called Krull's principal ideal theorem. It has many applications. Also it is very important in algebraic geometry for many applications, but before that I want to deduce two corollaries from the dimension theorem. So, we have deduced corollary 1, 2, 3. Now, today is corollary 4. Remember, dimension theorem is for the Noetherian local ring. Three definitions of dimensions are equal. One is the supremum definition, the other is the degree of the Hilbert-Sample polynomial, and the third one is Chevalley dimension. So, actually this corollary actually I have deduced in corollary 3, but this is slightly different flavor. So, as usual our notation is A M local. Local always includes Noetherian, and A is an element in the maximal ideal M, and V is finitely generated finite A module. Then we have seen if I go mod this element A, that is if I consider a module V by AV, and the dimension of this module can drop at most by 1. What extra I want to add here is if A is a non-zero divisor, for the module V, then equality will hold here, then equality holds. So, proof. Remember, when you say an element of a ring is a non-zero divisor for a module, that means the left multiplication by A on V, any x going to Ax, this map is injective. That is the definition of when you say A is a non-zero divisor for V. So, suppose A is a non-zero divisor for V, that means this A cannot belong to, okay. So, we have associated, look at the associated primes of V. This is a finite set, P1 to Pm, and obviously the dimension of V is then sup of dimension of A by Pi's, where I is running here, I is equal to 1 to M, because the dimension of V is the length of the chains of prime ideals inside the support of V, and any element of support of V will contain one associated prime, and among the associated primes also, if somebody is minimal, then we would go down to get the maximum length of the chain. Okay, so among them actually I will choose P1 to Pn, which actually gives the dimension such that dimension of V is attained at all these guys, that is dimension of A by Pi I is from 1 to n. So, this is a so choose, and because this A is a non-zero divisor, A cannot belong to any associated primes here, in particular any one of this. So, since A is a non-zero divisor for V, A cannot belong to any one of them. A cannot belong to union I is from 1 to n pi. So, therefore, if I look at V prime, let us call V prime to be V by AV, then support of V prime will definitely be contained in support of V and removing P1 to Pn. Because P1 for example is not in support of V prime, because when I localize this at P1, then that A will become a unit, therefore, this module will be 0. So, it will not be in the support. So, therefore, support of V prime is actually will not contain P1 to Pn, and therefore, the dimension of V prime will not come from any one of this, right. So, it will be bigger, it will be less equal to dimension of V minus 1, because it will drop at most by 1, and on the other hand it is this inequality. So, equality holds. So, that proves the corollary. Okay. So, this is probably the appropriate time to define. So, I want to make a definition. That suppose we have a non-zero module V and A1 to AR are elements in the maximal ideal of A. So, remember all the time our assumption is A is local and V is finite A module. Because we are in all the proofs we have been using associated prime, support, etc. All this will behave well when the module is finitely generated over a Noetherian ring. Okay, so this element A1 to AR is called A1 to AR is called an irregular sequence for M for V, if for each I from 1 to R, AI is a non-zero divisor for the module V by ideal generated by the earlier guys A1 to AI minus 1 V. So, this means for example, start with I equal to 1, A1 is a non-zero divisor for V. So, A1 this means, so that is A1 is a non-zero divisor for V. Next, A2 is a non-zero divisor for V by A1 V. A3 is a non-zero divisor for V by A1 A2 V, and so on. So, such a sequence is called regular sequence. Now, it is not clear from this definition at all that whether the permutation of a regular sequence is regular or not, or how does one test somebody is a regular sequence. So, this is the next topic I am going to take up with a lot of things which are called, some homological algebra will come and some other stuff will come, but just now I want to make a definition because I want to write one more corollary to the dimension theorem. That if I go modular regular sequence, so the dimension of V by A1 to AR V, this will drop exactly by R if A1 to AR is a regular sequence. So, dimension of V minus R if A1 to AR is an irregular sequence. For V. Already in corollary 4 we have proved this assertion for R equal to 1, and obviously we are going to prove this assertion for by induction on R. But before the proof, also in particular I want to write down, in particular a regular any irregular sequence for V is a part of a system of parameters for V. That means any regular sequence I can extend it to system of parameters, and system of parameters means is the D elements where when you go mod them the length is finite. So, the proof of corollary 5, that is by induction on R. R equal to 1 is corollary 4. So, the way the definition is made, we know the first R minus 1 elements will form a regular sequence for V of length R minus 1, and by induction hypothesis dimension of V by ideal generated by A1 to AR minus 1 times V, this dimension will drop exactly by R minus 1. And now I am going to apply once again corollary 4, apply corollary 4 to the module V prime equal to this V by A1 to AR minus 1 times V. Then by definition of a regular sequence, this element AR, then by definition AR is a non-zero divisor for V prime. So, by corollary 4, dimension of V prime mod ideal generated by AR V prime, this dimension drops exactly by 1 from V prime. So, now just put it together and then you get the corollary 5. Okay, now getting back to principal ideal theorem. So, this is very, as I said, this is very important theorem, and actually I want to give two proofs, one by using dimension theorem and the other is not using. So, for example, how did we prove that if I have suppose I have a Noetherian ring, a Noetherian, and P is a prime ideal, and then we have defined height of P, this is by definition, it is a sup of R such that there is a chain of prime ideals contained in P. So, that is P0 etc., 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 PR, this is a chain of length R and these are all contained in P, in spec A. Such a supremum we call the height of P, or sometimes also in a geometric language I think it is better to call it a codimension P. So, this I will just mention now, but later on when we switch to some geometric statements, it will be better to call it a codimension. Okay, but that is not important now. But from this definition, a priori it is not clear that this height is finite, and we have noted that this height is also nothing but the dimension of the localization, because we know correspondence between the prime ideals of prime ideals of localization and prime ideals of A. These are those prime ideals which will remain here prime when they are contained in P, and if they are not contained in P, they will contain a unit, and therefore it will not be a prime ideal. So we have a good connection. So actually this we can identify here with that. So after this, what we did was we proved the dimension of a local ring is finite, and that follows from the fact that it is by the dimension theorem, because we have proved that this Krull dimension is same as the degree of the Hilbert-Samuel polynomial, and degree of the polynomial is an integer, natural number. So it's finite. That is how the proof was. But I will prove today by using Krull's so called principal ideal theorem that this is finite. So let us observe some facts. There may be some repetition, but let us do it for the sake of simplicity. So let me write a lemma. So first of all, height of P is, now the first proof I will give by using the dimension theorem, and the second part I will not use the dimension theorem and prove height is finite. So first statement is height of P is less equal to mu of P. Now remember, my ring is not local, so one has to be little careful when one says mu of. So remember here, when I have a module V is an A module. What do you say about mu V? This is by definition. Look at all generating sets of V, and among them take the one which has the least cardinality. That is called minimal. That number is called minimal number of generators for V. This is called the minimal number generators for V. And remember, so this is slightly different from saying that you take a minimal generating set and take the cardinality. See, minimal generating set by definition means a generating set which you cannot remove any element from that. So that such a set is called a minimal generating set. For example, if I take A equal to ring of integers and V is also integers. So here 2, 3 is a generating set for V, and it is a minimal also, because you cannot drop 2, you cannot drop 3. So this is actually the minimal generating set. 1 is also minimal generating set. So the two minimal generating sets may have different cardinality, but among them we are choosing the minimal one. So in this case, mu of Z as a Z module is 1, and you would have seen probably that given any integer r, you can write down a minimal generating set for Z as a Z module for arbitrary r. So for arbitrary r, natural number, there exists a minimal generating set of cardinality r for Z. Okay, so I gave you example for 2 elements, 3 elements also you can do, and 4 elements also you can do. You cannot drop any one of them. This is a nice exercise. Probably you will need Chinese remainder theorem or playing with the prime numbers. Okay, so the first statement is height of P is less equal to mu of P. where mu of p is the minimal number of generators for p. And because we are in a Noetherian ring, every ideal is finitely generated. So, in particular p has at least one set which is finite set of generators. So, in any case mu p will be less equal to, this is a finite number. So, this also proves height, this proves in particular height p is finite. Okay, so, this is the first statement of the lemma. Second, if r is height of, so now it is finite. So, I will call r is, if r is the height of the prime ideal p, then there exists a chain of length r like this, which is p in spec. So, that means if you see that this height is r and then the other side is supremum, that means supremum is attained, right. Okay, third one, if r is height of p, then for each r, for each I from 0 to r, there exists a prime ideal pi with pi which is contained in p and height of pi is exactly I. Okay, so let us prove this lemma first. So, proof of the lemma. 1. I want to prove that height p is less equal to the mu of p. So, we have noted above height p is nothing but dimension of A localized at p. Now, A is a local ring. This is a local ring with the unique maximal ideal PAP. And we have noted that this dimension is the degree of the Hilbert-Samuel polynomial. But this degree, we have noted that it is, the degree is less equal to the number of generators for this ideal. You remember, if you have taken a Q to be M primary ideal in a local ring and then taken a module over that and defined a Hilbert function using that, then we have checked that the degree of the Hilbert function is less equal to the number of generators for the primary ideal. So, here the primary ideal is PAP itself. So, this is less equal to mu of PAP, minimal number of generators for the maximal ideal. But this is less, this is obviously less equal to mu p, because if you take a generating set for p, then after going to localization some of them may not be required. So, therefore, the minimal number of generators will be less equal to mu p. So, this is where we have used the dimension theorem. That the dimension of a local ring equal to the degree of the Hilbert-Samuel polynomial. Okay. So, that proves 1. So, 2, since height is finite, by 1, the 2 is clear, 2 is immediate. Because it's a finite number, and so okay. So, 2 is clear, and 3, you want for each I some prime ideal which is contained in P of height I. But you see, 2 says if R is height, there is a chain like this of length R and the last one is P. So, if I take Pi here, the height will be I, that is obvious. So, clear from or take Pi equal to Pi equal to the ith element in appearing Pi equal to the ith prime ideal appearing in 2. Okay, so that proves the lemma. Now, the lemma was for prime ideal. So, in general, if you have an ideal A in a chain ring, then one puts height of A. By definition, this is the infimum of heights of prime ideals P, such that P belongs to spec A and A is contained in P. But obviously, these are all prime ideals of the ring which contain all of A. But now, it is clear that we only have to concentrate on the minimal elements in the support, and minimal elements in the support is same as minimal elements in the associated primes. So, what I am talking about is support of A by A and associated primes of A by A. This containment is clear, and the minimal sets are same. Min support of A by A is same as min associated primes of A by A. When I say mean, you see these sets are ordered by natural inclusion. The mean means minimal elements. There could be many. It's not a chain. So therefore, height of an ideal A is minimum of, and now I want to use a minimum word because infimum word is usually used for an infinite set. So when the set is finite, then one uses the word minimum. So minimum of height P, where P is minimal over and minimal over A means an element of the support which is a minimal element there. That means so this means there is no prime ideal in between A and P. There is nobody here in between. If somebody is there, then it has to be equality here. That means the minimal, there is no prime ideal in between A and P. Okay. In particular, there are finitely many elements, therefore, in particular at least one element. So, in particular there exists P, prime ideal P, which contains A and height of A is equal to height of P. Such a P will be necessarily minimal. P will be necessarily minimal over A, because if there is in between, the height of P will increase, height of that whichever is contained, his height will increase. So, therefore, it is minimal. Okay.